This is part two of the event discussion, February 26th to March 1st, 2024. We'll talk about three events in this part two. The first one is Thierry Tambe, New Frontiers in Chip Design for AI. He talks about several attempts to either save power or memory or both in modern AI workloads. What I find interesting about Thierry is really he's at the crossroads of engineering and AI. So he understands AI, he understands engineering, and he's actually a proponent of a full stack integrated approach towards chip design, which incorporates every aspect of the stack, starting with the application all the way down to the physics of the layer. And this is very much Onur Mutlu type stuff here. And what I like about Thierry also, he's kind of fresh off the PhD. So he talks about his PhD and he applies his PhD to real tape out type solutions. So his main ideas are quantization. So that means you can sort of reduce complexity by having less information to process, but not losing information. Precision, adaptation to workloads. So do we need floating point? He talks about the fact that we have a lot more requirements of a special precision in modern Gen AI workloads than before, and that requires a different approach because otherwise you just have a lot more energy and power consumption. eDRAM is a solution to that, where you have this goes down the route of flash attention, which is it's not the same solution, but it's the same problem, which is that we have massive amounts of memory requirements in the processing of training and inference in Gen AI. And one solution is DRAM on chip, because although you need to refresh, you might be able to get away with less refresh cycles because the data is transient. Sentence level granularity and voltage frequency adjustment, that goes into the question of, this is really fascinating. I mean, this almost touches upon Dorsa stuff, which is like, okay, look, how much information is there in a certain query or in a workload, or let's say a query, right? What's the entropy of the query? How complex is it? And the more complexity you have, the more frequency you need, the more capacitance you need. So he breaks down if you think about an algorithm, and if you take, let's say, Onur Mutlu's lectures, he would talk to you about sort of the conceptual way DRAM works and how, let's say, a workload accesses information. Thierry talks about this and goes really down to the physics. For example, he talks about implicit refresh, which means the way you approach data in DRAM is, let's say, through the bit line, and then you look for the particular bit. And while you're doing that, you could also that voltage which is necessary to go grab that bit could be used to refresh the bits around it. So there's an implicit refresh, less cycles of refresh, less power consumption. To me, that's really fascinating stuff. It's, in a nutshell, a full stack approach towards chip design, which again I find very fascinating. The second presentation I want to talk about is Renee Zhang, magnetically actuated origami robots that can crawl and swim for effective locomotion and targeted drug delivery in severely confined spaces and aqueous environments. I think the main takeaway here is that you have different approaches towards the physics of a robot. For example, you could use origami style materials that can move through magnetic motion, and you could control those magnets with algorithms. So to me, that was interesting in terms of drug delivery, of course, but also or any kind of constrained environment. But it's also interesting, let's say, why don't we have origami style arms for robots, actuators for humanoid robots, for example? It'd be interesting. The third one is Emily Alsentzer, creating datasets for few-shot learning in rare disease statistics. This is a sort of a statistics by statistics lecture, and interesting always to see how people deal with specific problems of, let's say, few-shot learning in rare disease situations. Of course, goes down to, okay, how do we in general solve problems where we don't have a lot of data to train on, but we still want to have more accuracy in inference. This is not in the wrong podcast. It's March 2nd, 2024. This is Krim Delko. It's a Saturday. There is no update for the year. We are down 8.5%. The market is up 7%. We're underperforming by 15.5%. So this is the second installment of this week's events. We're going to talk about three presentations. And the first one is Thierry Tambe, New Frontiers in Chip Design. Thierry, I've discussed him before. Thierry is a new, just recently appointed professor at Stanford, but he's also at NVIDIA. So I find him really fascinating because he has that absolutely encompassing approach towards chip design. He's an electrical engineer with a algorithmic thought process, and this is exactly what's required in this modern area of Gen AI. So what that means is really like he thinks about the application, he thinks about the algorithms, the data structures, and then he thinks about the microarchitecture and then the design of the chip. So he tries to encompass all of the aspects of the values of the workflow that goes into training and inference in AI. And I think this is it's a big task. His PhD is encompassing lots of ideas: quantization, precision adaptation, eDRAM, sentence level granularity and voltage frequency adjustment, entropy, exit, implicit refresh of DRAM, lots of ideas. And I think in order to keep this podcast, this podcast series, the purpose of this podcast series is to give people a sense of what it feels like to run a hedge fund. It's not to understand electrical engineering intricacies of chip design. So I have to try to keep it at a level where it makes sense to dive into the technology, but it's also at a level where you can apply this to, for example, investing, or at least understanding what the competitive dynamics will be in future chip design, manufacturing dynamics, things along those lines. So that's the goal here. And I think Thierry is a very good, actually, example of how this can be done, because you can go very deep into the granularity. For example, implicit refresh means, okay, how does DRAM work? And when we go and fetch certain data points, maybe we can organize it in a way so while we're fetching those particular bits in particular DRAM cells, we want to do it in a way so we also have implicit refresh, which means that the voltage applied towards fetching certain types of bits can also be used for refresh. Maybe we want to be a bit smarter about how we do this. Now, this is, of course, an electrical engineering problem, but at the big picture, you can say, look, there are lots of ways to save power, and power is the big constraint. And the reason power is the big constraint is there has been, recently I've seen a chart which showed that an inference in a traditional Google search, for example, let's say is, let's just say 1 unit of energy, and then a Gen AI type inference is like 100 units of energy. So it's orders of magnitude more. And that, of course, is just the beginning. We're talking about multimodal type Gen AI. We're talking about robotics. We're talking about physical we're talking about dealing with physics. So we're going to have to deal with a lot more data, a lot more energy consumption, and therefore it's worth looking into this now. So let me talk about some of the ideas. Quantization means, and this is something NVIDIA has been working on for years now, it just means that can we reduce the amount of data that is being processed by not losing any information. Sort of if we have something which is close to zero, then let's leave it at zero and not even process it. And if something is very close to one, then that's very important, and we should process it maybe and pay more attention to it. Precision adaptation, this is really interesting. Thierry shows a chart where he's just a dispersion of weight formats, or in other words, the numbers in the matrices in sort of a masked autoencoder type architecture is just much more dispersed, right? So that means you need more precision when you calculate all these things. But and that's fine, but you don't want to apply that precision for all the data points, only the ones which are necessary. So you need some adaptive, some gated, form in the silicon to understand when you should use more precision and when less precision. eDRAM is a really great idea. It means that you can have some sort of volatile, cheap, and very dense storage on chip, because a lot of the data is transient. So you might get away with less refresh cycles than maybe you should use normally for something like DRAM, because it's transient and you can sort of gain in density, cost, and power consumption, versus using SRAM, which according to Thierry is maxed out in terms of scalability. I don't know why, but that's the case. Sentence level granularity and voltage frequency adjustment, that is another very interesting sort of how should I say, it's an interesting approach, right? What Thierry does in his PhD, he dissects the workload of a particular process on chip in frequency, capacitance, voltage, like the components that are necessary to execute a certain workload. And now we can start thinking about, okay, how much frequency do we need for what type of data format? And I think in a nutshell, what he's trying to say is that if we have a lot of entropy, a lot of, if my prompt's very complex, okay, if I ask something really complicated, then I need more energy to process that than if I ask something less complicated. So maybe I can ask something a bit less complicated, but still keep the information content of the prompt intact. This goes really into the direction of Dorsa, which is, and what her collaborator, Erdem, I think is his name, what they work on, which is what are efficient ways to ask questions? What are efficient ways to do pairwise, contrast learning? Like, all these things are related. And why are they related? Because you have fundamentally the problem with sentence level granularity is, look, I can keep it pretty complex and I need a lot of energy to get the work done, or I can maybe simplify my complexity and have less energy requirements to get the same job done. This is, in a nutshell, what Thierry is trying to approach here. And I find that very interesting because it forces you to go into the whole stack, right? To understand each particular component of the stack and then analyze where you can maybe be more efficient, and it doesn't necessarily have to be on the chip design level. So overall, I think where this is going, I think in the end, it's going towards what Jensen Wang keeps talking about, which is, okay, if we can have abstractions at high level and connect that to the physics and the actual silicon, then we can iterate around these abstractions and find the most efficient ways to design chips, which in the end is the goal here. The second presentation I want to talk about is Renee Zhang. Now here, she spoke about magnetically actuated origami robots that can crawl and swim for effective locomotion and targeted drug delivery in severely confined spaces and aqueous environments. I wasn't very impressed by the presentation because I feel like it was a mechanical engineering type presentation, which is fine, but I think what we need in robotics is a little bit more than just efficient actuators, and that's really what she was talking about. So yes, it's certainly an important part, and Tesla is working on this day and night. Cheap actuators, scalability, all these things matter. And what Renee is suggesting here is, think of an origami with magnets that can be manipulated, and then the origami can move based on those magnets. That's the idea. She can use it for drug delivery. She's doing some tests with mice. I thought it's worth mentioning, certainly worth sitting in and listening. But overall, I thought that maybe she should add more algorithmic work also, or think about it at least conceptually, how this could help solve problems, and again introduce algorithm. But maybe also I didn't quite understand. Maybe I'm just not giving her full credit. Again, interesting, definitely worth mentioning. And the third thing I want to talk about is Emily Alsentzer, create data sets for few-shot learning in rare disease statistics. This is an interesting presentation because it's really about data augmentation. So what Emily is trying to solve is the problem that you have rare disease patients, and you'd like to diagnose them. So you have people, they come with certain phenotypes, certain effects, and you think, okay, maybe you have this disease or that disease. And because the type of effect that you see, the phenotype, might be related to a certain gene, maybe it's a monogenetic disease, but you don't have enough data to actually train. So what she's doing is she's augmenting. So she's using a data set. So she's simulating patients. And quote, the simulated patients used for training are created using an adaptive simulation approach that provides realistic rare disease patients with varying numbers of phenotypes and candidate genes. So think of this is data augmentation. Like if we use this, let's say, in the self-drive space, I mean, this goes a little bit into the direction of the Peter Bill et al. Paper that was published last week about using generated videos for robot learning. What you're trying to do is really embed a generated reality into the actual reality, and then create a lot more data and then learn from there. That's really what she's trying to do. And she's doing something that I think the robotics people are trying to do, something that pretty much everybody probably will do sooner or later, because with Gen AI, we have the ability to generate data sets that are embedded in reality. So that's the whole idea of Gen AI. I mean, you start with a prompt, and the model's trained in reality. So when I let's say, back to the video, if I have a road in Palo Alto, I can train the model based on that road, and then just create a lot more dispersed variations of that road with a lot more dispersed events, and some of them are maybe Harry Potter events, very unusual. But if you sort of look at the Monte Carlo simulation here, you could have maybe a Gaussian or something where the bulk of the events actually really makes sense, and it's all embedded in reality. And the same is applicable here in the rare disease space. So I think that's why I thought this presentation by Emily was interesting. She's in the biostatistics space, and it's interesting to see that they're using very similar methods out of necessity. So to summarize the three events in this part two, one is Thierry Tambe. He talks about AI chip design in the modern world of AI, which requires a full, comprehensive, full stack view of things, and understanding workloads, understanding algorithms, understanding on the one hand, and on the other hand, understanding the physics and the actual technologies, the capacitance, the voltage, the frequencies used to execute workloads, and then find interesting ways to optimize along those vectors. Renee Zhang, magnetically actuated origami robots. This is, in my opinion, most interesting just in a sort of more general way of understanding how we could have different actuators, maybe magnetic actuators with origami type materials. And third, Emily Alsentzer, create data sets for rare disease patients. I think this, to me, really is interesting from a perspective of statistics and data augmentation, and maybe in the future, a GenAI type data set creation for all kinds of problems, whether it's rare disease detection or robotics. And the idea here is that you have an embedded model in reality that you can then use to generate or bootstrap lots and lots more data and then train on that data set. Thank you.